In this video, we're going to be talking about the angle condition. We looked at it last time in Euclidean geometry, and we found that it was not enough to make the triangles congruent, that we could get some similar triangles. Let's see if that holds for hyperbolic geometry. So far in everything we've looked at, hyperbolic geometry has acted just like Euclidean geometry. Let's see if that still holds here. All right, so this one's a little tricky. So we put an angle here, and we can, move that around. We can also change the size of it. Then we pick a point there and make an angle there. And we pick a point C of the red on the here, and we get this. Now what do we have to do? We have to manipulate these points until the red and the blue are on top of each other. And the question is, how many places does that happen? So basically move B in and out, and A in and out here, or that one in and out. And it's actually quite difficult to get this to match up. Okay, so it's pretty difficult to see this in this particular one. But that's what we'd have to do. I actually had it pretty close a few minutes ago. It's hard. See, I'm just manipulating this thing and trying to see. Well, the question is how many places? It's not clear that it's infinitely many places like we had before. And it's not going to be completely clear from this exploration. But I want to try to convince you that it turns out that the trouble is I got two different controls to try to keep working. Okay. But it turns out there's exactly one spot that it's going to meet probably. Oh, there's really close at least. So it turns out there's only one place that this is going to happen. So it turns out a little harder to see in this application than in some of the others. But it turns out that in fact in hyperbolic geometry, if you can get the angle, all three corresponding angles to match up, you're going to actually get the two triangles to be congruent. And angle is not the same as angle in this one. In Euclidean geometry, if you actually have two triangles that exist and you have two pair of corresponding congruent angles, the third pair of angles are going to be corresponding and congruent as well because of the triangle angle sum theorem. But we do not have a consistent angle sum in hyperbolic geometry, so that doesn't work. And it turns out here that angle does not give you a third angle. But if you've got all three angles congruent, then in fact you do get a one congruence class, and all those triangles are congruent. You can get this where it's not possible, and of course it's the same condition we always have had. If these add up to be more than pi radians when you add these all up, there's not even going to be a possibility for this ray and that one to meet, no matter where B is. See, even if bring it all the way down, it's not going to work. So we can make a zero possibility. That's when the three angles add up to pi or more than pi, that is 180 degrees or more. There's no solution. But if the angles add up to less than pi, less than 180 degrees, then there's exactly one congruence class of solutions. So the angle criteria is enough for hyperbolic geometry. It's actually a little bit more, a little bit stronger than what we have in Euclidean geometry. Also, something this points out is there's no such thing as a similar triangle in hyperbolic geometry that's not congruent. Okay. Because remember what similar triangles are is if all the corresponding angles are congruent and the sides are proportional. Well, here, if all the corresponding angles are congruent, the sides are not only proportional, they're actually congruent. So I guess it is a similar triangle, but with a scale factor of 1, it's actually just congruent. So there's no such thing as similar triangles that are not congruent in hyperbolic geometry.